Welcome to Calculus. Today we will investigate finding one-sided limits, focusing on right-hand and left-hand limits of step and piecewise functions. Let's take a look at 3 examples. We'll head over to our notes screen. So our first example is a step function, and we've got 2 tasks. We want to graph the step function by creating a table of values, and then we want to evaluate the one-sided limit. So let's take a look at the table of values to begin. And we have in the past used -2 through +2. For a step function though, what I want to do is be sure to include some decimal values in between the integers. Now I need to kind of catch where I'm looking for the limit. So the limit is around +2. There is a power of plus up to the right, which we got to interpret in a moment. But to begin, I'm just going to put kind of a small slice, 0. I'm going to include 0.5, 1, 1.5. So notice I'm including half increments. And we'll go up to 3. Let's calculate the output. So again, I'm just going to substitute those values into the function. So f at 0 is going to be the step function of -0 plus 1. Well, that's just 1 on the interior of the step function. So recall what the step function says is what is the greatest integer that is less than or equal to the interior of that step function. So what's the greatest integer that's less than or equal to 1? Well, that's just 1. And that would fulfill the equal to part, less than or equal to what's inside there. Let's see what we get when we have a decimal. So f at 0.5 is -0.5. I put the parentheses really because just in case that input was -x, it would give me a correct sign change. Here I probably don't need it, but I do it. So -0.5 plus 1 is 0.5. So we want to consider on a number line, if I were to place 0.5 in its spot, so that's 0.5, and the integers are the ones in green, so 0, 1, and 2. So those are the only possible outputs. The floor function just gives back integer values. So I want to say what's the greatest integer that's less than or equal to 0.5? Well, for floor function, that's over to the left if you got a decimal. So what we're looking at as an output is 0. Let's calculate for f at 1, see what that looks like. So f at 1 is negative parentheses 1 plus 1. -1 plus 1, 0. So anytime I have an actual integer in the step function, it evaluates as that number. Now I'm going to notice I've got a duplicated output. Let's see what happens at f at 1.5. So f at 1.5 is -1.5 plus 1. So that's going to become inside the step function -0.5. And the closest or the greatest integer that is less than or equal to -0.5 is going to be -1. All right. F at 2 is step function -2 plus 1. And that's going to be -1 inside the step function. So again, that bumps that out. So I'm seeing a pattern here, and I can, at this point, probably predict, I think f at 2.5 is going to be -2, just based on the pattern I see in my table. What would you predict f at 3 to be? Good, -2 again. So we start to see that with that regular increment of 0.5 in our domain values, each pair of outputs are going to be the same. Well, let's graph this. So I've got the point 0, 1. So that's right here on the y-axis. And then at 0.5, it's down on the x-axis at 0. Same at positive 1. At 1.5, it's at negative 1, as it is at 2. So that's kind of where we're looking for our limit, is around 2. Down here below, 2.5 is at negative 2, as is 3. And really, I could continue this pattern across the whole coordinate plane. And I could do that up until the end. So definitely on these steps, you can kind of see the steps forming. The right-hand side of each step is a closed point. The question is, what's on the left-hand side? So when we get to the left-hand side, we bump up. So on the left-hand side of the step, what's that value? Good, it's an open circle. So the domain is really unrestricted. It's got all the x values, but the y values are restricted to just integers. So in general, the left-hand side on this particular one is going to be open circle. And we can complete that graph with this same pattern throughout. It's very consistent. All right, so there's our graph. There's our graph of this step function of negative x plus 1. It definitely has the appearance of a linear function, but with these continuous line broken into parallel steps. Let's evaluate the limit. So we completed that first task. Let's say what the limit's asking. So it's got this, the limit as x approaches 2, but then it has that power of plus. What's the power of plus mean? This means find the limit as x approaches positive 2 from the right side. So that power of plus, really, it's about which direction am I going to approach the limit. And that is what we're really investigating with this segment, is how do I find the limit just from one direction? So we've worked in the past limits from the left and from the right. And we'd even claim that if those aren't equal, the limit doesn't exist. But we can take limits just from one side. So that's what we're asked to do here. So let's look at our graph. Here's 2. So if I'm coming from the right-hand side, the question is, am I going to be at the level of negative 1 or at the level of negative 2? Well, the right-hand side is from the level of negative 2. And notice I can't actually say that f at positive 2 is negative 2. It is negative 1. But if I'm coming from the right side, I'm still on that level of negative 2. Let's go ahead and record that. That's the limit as x approaches 2 from the right of the step function negative x plus 1 equals negative 2. Let's take a look at one more example. Let's take a look at one more step function. So this step function is the limit as x approaches negative 3, also from the right, of greatest integer function 2x plus 2. Let's start again with our table. And we got to notice that I'm multiplying x by 2, so we probably want to ask at the outset how that's going to change our graph. And really, there's probably two options. Is it going to make the steps broader, or is it going to shrink the steps, make them narrower? So you can make a prediction. What do you think the 2 will do to the width of the step? But let's carry it out inside a table. So I'm going to go negative 4 as a start for my domain values, but I should go ahead and include the decimal values in between the integers. So I'm going to go negative 3.5, negative 3, negative 2.5. -2, -1.5, -1, -0.5, and 0. The reason I'm choosing those specific ones is that they kind of center around that limit value that I'm looking for. So you kind of respond to what the limit value is there when you're choosing your x values. Let's evaluate. So I'm going to pick up f of x. So let's start by calculating f at -4. And that equals, in parentheses, 2 times -4 plus 2. So 2 times -4 is -8, plus 2 is -6. And again, what we're saying is, what's the greatest integer that's less than or equal to -6? Well, that's -6 itself. F at -3.5. 2 times -3.5 plus 2. These decimal values are the ones that are really going to kind of give us some insight into how the steps are set up. So 2 times -3.5 is -7, plus 2 is -5. And again, that's an integer, so it places us right at -5. F at -3 is 2 times -3 plus 2 inside the step function. 2 times -3 is -6, plus 2 is -4. So what we're seeing is that with our increments of half, I don't have the duplicated y values. They're just going up by integers by the halves on the domain. So I think that f at -2.5 is going to output -3. F at -2 will output -2. F at -1.5 be -1. And again, I'm doing this based on the pattern that I saw. Our domain hasn't changed its increments. We're going up by halves. And the first few values that I calculated went up by integers. So I'm just continuing that pattern with predictions here. All right, so that gives us ability to graph. Let me fix that last value. I counted down instead of up, so we should go at 2. So let's graph what we have. So at -6, that's at -4. So that is a closed point. It actually equals that. At -3.5, it bumps up to -5. At -3, I'm at -4. -2.5 is at -3, -2 is at -2, -1.5 is at -1, -1 is at 0, -0.5 is at 1, 0 is at 2. And those are the points that I evaluated in the table. I could continue that pattern, just kind of noting how it looks geometrically, and continue down here. The question is, how do I fill in the steps for the function? So since we're really interested in what's happening around -2, what I want to calculate is something in between -2 and -1.5. Why did I choose that side of -2? I'm sorry, let me back up. I'm thinking about the last problem. We're looking at -3. So I'm really wanting to calculate in between -3 and -2.5. So why didn't I go between -3 and -3.5? Well, I am calculating a limit from the right-hand side. So I'm just going to fit that in here with this blue color. So f at, let's go -2.75. That's a value in between -3 and -2.5. I just want to see, does this bump us up or bump us down? Do I stay at -3 or go to -4? So I'm going to plug that in the limit. So +2 times -2.75 plus 2. And then we want to evaluate that. So 2 times negative 2.75 is negative 5.5 plus 2, which equals, in the step function, negative 3.5. So when I think about the output there, the output is going to be the greatest integer that's less than or equal to negative 3.5. We go to the left, that's negative 3. I'm sorry. To the left is going to be negative 4. Let me get my number line straight. So I'm going to graph that point just to see which way do the steps go. Do they go to the left or to the right? So that's at negative 2.75. And that's at negative 4. So it looks like, based on this graph, I've got the closed point on the left of the step, the open point on the right. Well, let's fill that in. So right here is kind of where we're really thinking about. And these are close quarters, but we can make it work. Left-hand side is closed, right-hand side is open. And that continues down below as well. So I'm going to fill in these steps. While I'm doing so, how did your prediction go? Did that multiplying by 2 make the steps broader or narrower? Good. It made them narrower by half. And really what we can think is that if I were to kind of draw a line through that step function, its slope would roughly be positive 2. Of course, the step function pulls that line down into individual parallel steps. All right, so we've got our graph there. We need to evaluate the limit based on what we see in the graph. So again, we're saying, what's the limit as x approaches negative 3 from the right? So here's the x value of negative 3. And what we're looking at is, what is the y value as we approach the x value of negative 3 on the function from the right-hand side? Well, it looks like that is the value of negative 4. So the limit as x approaches negative 3, again, that power of plus means from the right-hand side of step function 2x plus 2 equals negative 4. Remember, the limit is the y value as x gets close to a certain number. Okay, so that's a couple examples using step functions. Let's take a look at our last example, which is a piecewise function. So our task starts the same. We want to graph this piecewise function and then evaluate a limit. In this case, what happens to the y value when x gets close to 2 from the right-hand side? We'll do so from the graph. So again, I'm going to start with my x column, and I'm going to look at the threshold. So I switch from one function in the piecewise to the other function at the x value of 2. So 2's got to be here, kind of central in my domain. And I also want to include a third column. So remember, with piecewise functions, we've basically got two functions that trade off at a certain x value. So I'm going to put, let's go back up to like negative 1 on the left, and then we can zoom forward to positive 4. In fact, let's go to 5. And then let's evaluate. So for the first function, when x is less than or equal to 2, so I'm talking about those three values, 2, 0, negative 1, the function is x over 2. So let's evaluate those outputs. So this is going to be negative 1 over 2. I'm just replacing negative 1 for x. So that's, as a decimal, negative 0.5. 0 over 2 is just 0. So that's right on the origin. And then 2 over 2, oh, you know, I have a hard time counting sometimes. Let's make sure we catch 1 in there. And we'll adjust all this. Okay, so again, we're going from 2, don't skip 1. Let's fill in. So this is going to be 1 over 2, which is half, and then 2 over 2, which is 1. And that's that point when x equals 2 that we switch over to the other function. So the other function is x squared, the parent function for quadratics. And it really doesn't ever equal 2. Notice that it's strictly greater than 2, but the trade-off is right there. So I'm going to pretend like I'm going to evaluate 2 squared, and that's 4. But I'm going to put in parentheses because that's not part of the green function, but the green function comes up to that value from the right-hand side. We'll use that when we calculate the limit. 3 squared, however, is on the function. So we got 9. 4 squared, these are going to be difficult to graph. 16, 5 squared, way off the chart, 25. So let's graph that piecewise function. So here at -1, it's at -0.5. Goes through the origin. I'm going to back up. I'm graphing in the wrong color. So again, -1 is -0.5, 0, 0, 1 half, and 2, 1. So the left-hand side of this piecewise function zooms over there to the left. The right-hand side is the right hand of the parabola. So at 2, it starts at 4. At 3, it's at 9. And then what we noticed was it really is off the page. So I'm going to start here. I do need to adjust what I've put there at 2, 4. Should that be an open or a closed point? Good, open. And again, that's because this is strictly greater than. So that's that right side of the parabola. So we've graphed the piecewise function. What we want to do is calculate the limit. So the limit, if we look at the way that it's written, is what's happening to the y values. X gets close to +2 from the right side. Well, that right side is going to be this green kind of part of my quadratic parent function. So what I'm saying really is, what y value is this getting close to as x gets closer and closer to 2? Well, that's right there in our table. Notice we calculated it. It's not part of the function, but it would be part of the function as a limit. So we can finalize our answer here. The limit as x approaches 2 from the right-hand side of f of x. So I'm just going to call the whole function f of x. See how that's given in the question? Equals, so as x gets close to 2, y gets close to 4. All right, thank you for joining for these 3 examples of finding one-sided limits using step functions and piecewise functions. Thank you for joining. See you soon.